Okay, the dignity shown in these various photos perhaps is a reflection of the quality of the message here. But Deborah Goldberg earlier referred to sort of speaking, looking down from 30,000 feet or so, and today I'll maybe be looking down from 100,000 feet, perhaps obscured by Sirius clouds or something. But in any event, I'd like to talk about patterns of diversity, geographical patterns of diversity, and if we go back at least as far back as Linnaeus and the subsequent naturalist explorers of the 18th and 19th centuries, we've had this understanding, this very coarse understanding of the tropics being this intense place of sometimes colorful, sometimes nasty, invariably intricate biodiversity relative to the temperate zone. And ever since the first very general observation of this geographical disparity, ecologists, biologists have had two different types of explanations for why we should see these kinds of differences. And I'm going to broadly characterize them as equilibrial explanations and non-equilibrial explanations. So, for example, in 1878, Wallace says, as we approach regions of polar cold or desert aridity, the variety of species regularly diminishes. More and more are unable to sustain the extreme climatal conditions. So the idea being in these equilibrial hypotheses that there's some characteristic of the physical environment in a particular locale or region that potentially determines the number of species that that locale or region can support. Now at the same time, and in fact in the same paper by Wallace, an alternative view, a more non-equilibrial view was espoused. In this case he says, the equatorial zone exhibits to us the result of a continuous and unchecked development of organic forms, while in the temperate regions there have been a series of checks and extinctions. And so he also goes on to basically say that the temperate zone has not had a fair chance for evolution to proceed because of things like glaciations. Now, although both of these views were recognized, and again, here even by the same person at the same time, from the beginnings of the recognition of these diversity patterns for 150 years or so, the non-equilibrial sorts of views dominated thought, to the extent that biologists were actively thinking about these questions of geographical variation diversity, and for the most part they weren't. That wasn't a major focus. But I think that it's fair to say that these non-equilibrial and historical explanations held more sway. In 1959, Hutchinson published a well-known paper called the Homage to Santa Rosalia, in which he kind of drew attention, renewed attention to these geographical patterns of diversity. Why do we have so many species? And in particular, he made an explicit call for that these diversity patterns are an ecological problem, and that they called for equilibrial explanations, and especially explanations rooted in energetics. So things related to food chain length, body size, productivity of the environment, these sorts of variables, area. And in fact, in the time immediately after this paper was published, well, I'm sorry, let me just mention that at the time he published that paper, biologists, ecologists were still very much thinking about the geographic patterns of diversity in a fairly coarse context. And just in that immediate decade following the publication of Hutchinson's paper, we started to get slightly more colored in pictures of what these patterns of diversity look like. So for example, Fisher compiled various distributional information in 1960 for various groups showing more specific quantitative latitudinal gradients, including things in the marine world. And Simpson in '64 published a large diversity map of mammals of North America showing these isopleths. Cook followed in 1969, doing something similar for birds. So we started getting a better picture, and in many cases seeing much more subtle complexities to these diversity patterns than simply a latitudinal gradient. But in the couple decades that followed, largely due to the influence of Hutchinson's student, MacArthur, the field really experienced a pretty dramatic shift towards focusing on equilibrial explanations, and couched largely in terms of the importance or potential importance of competition, focusing on modeling that competition and detecting the effects of that competition. But despite this sort of shift in the discipline and this renewed focus on equilibrial dynamics, for the most part, those equilibrial theories were couched in this form of limiting similarity rather than the energetics perspective that Hutchinson was calling for. And so in 1981, Jim wrote this paper, which has already been alluded to. And in my sense is that Jim, he had witnessed the growing frustration and limited success of those previous couple of decades, and so he was calling for renewed attention to something that he saw Hutchinson originally calling for, that again had not received as much attention, and that's this idea of energetics and the idea of equilibrial hypotheses, and specifically these two types of capacity rules versus allocation rules, which Pablo mentioned before. So, what has been the legacy of this paper, and how has our understanding of diversity patterns changed over the past 3 decades? Well, with respect to the capacity rules, I'd say that in the years immediately following the publication of Jim's homage, there was the development of species energy theory. Subsequent to that, especially in the past 15 or 20 years, there's been a cottage industry of documenting empirical relationships between patterns of species richness and various energetic or climatic variables. And that's in large part been due to the great eco-informatics initiatives that have allowed us to collate distributional information and generate these global maps, not just for well-known taxa like birds and mammals, but increasingly for less well-known things, including all kinds of marine organisms, terrestrial invertebrates, etc. And so empirically speaking, with respect to those capacity rules, I would say we've made a good bit of progress. And then again, as Pablo alluded to, I think perhaps we've made a little bit less progress on what he calls the allocation rules. Species abundance distributions, of course, have been studied for a very long time, and it was thought that perhaps this, understanding the secrets of this distribution and the subtle differences in shape might reveal the secrets of the underlying processes. I think we've come to realize that increasingly that's a very difficult proposition to arrive at concrete conclusions about those processes. Body size and metabolism, how that affects how energy is apportioned. Again, we've heard about some of those things today. But overall, I think how a given amount of energy in a particular location ends up getting divided the way it is across the different species that coexist there still remains a fundamental problem. Now, following the publication of Jim's 2 decades of homage, again, I think in partially in sort of a response to the couple decades of limited success following up on a lot of ecological theory, there began to be a slight backlash, maybe that's too strong a word to call it, but a re-emphasis towards more historical and regional perspectives on diversity. So people like Rickliffs and others emphasizing larger scale phenomena that perhaps are simply the contingent on the historical trajectory of a given location. And I think that began to gain prominence and sort of steal back a little bit of attention. In just a little over, I guess 11 years ago now, Hubble published his book on unified neutral theory, and I think that brought some renewed attention to a different type of equilibrial theory of species diversity that served as a focus for a lot of ecology for quite some period of time, and still remains a fairly large focus. But just in the past 5 to 7 years, I would say that a new paradigm has been growing, and that's this idea of phylogenetic niche conservatism, which I would categorize as a historical or non-equilibrial sort of explanation for why we see a lot of the latitudinal gradients that we see today. So that's my personal impression of how through the past 200 years there's been this shift of focus from equilibrial explanations to non-equilibrial explanations. And the reason that, or I guess the point I'd like to make in my homage to Jim's homage is based largely on this quote here from that paper, where he says, "I will assume that the goal is to construct an equilibrium theory for reasons both heuristic and practical. It is easier to understand the effects of historical perturbations from a conceptual framework that assumes eventual equilibration of rates of origination and extinction." And I think that's something that has underlain a lot of Jim's research and philosophy, is the search for general underlying principles, things that are repeatable, as MacArthur emphasized. And I think that pursuing these sorts of equilibrial explanations is a worthwhile thing to do, because from my perspective, at the very least, at a very broad level, most ecosystems are typically in some form of energetic equilibrium. And that may be a fun conversation to debate and hash out later over dinner, but I'll just pose two simple examples. And one is, on the left we had two small pieces of watermelon that some teenage girl in South Africa put out in her backyard for an hour just to see what would happen. And an hour later it's covered in all of these sorts of ants. And so I would argue that any resources that are easily metabolized, easily utilized, and predictably encountered in the environment are going to get used. They're going to get used by something. And so living things are energy transformers, and that energy is going to get transformed if things can find it and encounter it predictably. The second example involves parachutes. And at least up until recently, parachutes were made of nylon. Nylon is a completely man-made synthetic material which did not exist. That chemical compound did not exist on planet Earth until the year 1935. By the year 1975, bacteria were discovered, who knows when they actually evolved, that could metabolize nylon, right? So nylon we don't think of as this energy source that's something readily available, easily metabolizable, but even so, things figured out a way to utilize that energy. So energy gets transformed. And so, that's the capacity rule. So again, focusing on when and how these kinds of energetic equilibria get translated into diversity equilibria, I think is really what we want to understand. And when I talk about equilibrial explanations, it's important at this point to kind of cast aside this very coarse equilibrial versus non-equilibrial dichotomy, because there's a lot of other ways to slice and dice and categorize ecological theories. And so one example, of course, that has already been alluded to is this idea of local versus regional scales. And while in some people's minds, they kind of equate local with equilibrial and regional with historical or non-equilibrial phenomena, of course, you can have all combinations here of ecological theory. And yet another orthogonal axis by which we can slice and dice these theories is deterministic versus stochastic. And again, we can have all different kinds of combinations. And so the argument that I would make is that if we want to come up with an equilibrial theory, that perhaps in the past we have been very limited in focusing on maybe just a single one of these boxes at a time, but in fact a robust equilibrial theory of species diversity might at the very least include something from each one of these four boxes. And so combining those together is one of our challenges. I'm not even going to talk about the data. That was just a minor example of an attempt to do those sorts of things. But basically, I think that a lot of ecological research right now is along this path of integrating either across scales or integrating across dimensions of biodiversity, integrating theories such that the predictions are not just how many species there are at a given location, but other aspects of community structure, whether it's predicting something about the species abundance distribution, predicting something about species turnover in addition to species richness, making predictions about the slope of species area curves, etc. But lastly, I just want to emphasize that I do think that these energetic constraints on communities are important, and clearly they're not the answer to everything, but it seems like they're a fundamental element in this master equation that we're searching for. So with that, I'd just like to thank Jim for really providing, not only being a great mentor, but providing such a wonderful environment. He fostered such a great lab, a great group of people, and it was really a privilege to do my PhD in that environment with him. So, thanks.